Hi learners, it's Em from Sononerds, and this video is going to be on beam anatomy. Unit 9, Beam Anatomy. Just as we discussed the anatomy of the transducer using a simple single element, we'll use the single element transducer to discuss how an ultrasound beam looks in space. Note that this is going to be overly simplified for our initial discussion. We'll add some more things to consider in regards to more modern transducers at the end of the unit. For the time being though, the following diagrams are all referring to a single element transducer that is operating as a continuous wave. A single element transducer is going to create a beam that changes shape as it moves away from the transducer. It'll begin as the same size of the element and then start to converge to a natural focus. And then in the far field, it'll begin to diverge. Diverge means to widen, which it'll do so indefinitely until it attenuates completely. As we learn about the sound beam anatomy, focus, pun definitely intended, on these few things. We're going to look at the names of the areas that are within a sound beam. So I want you to know any alternative names that come up with it and how all of these areas relate to one another. You should also be able to describe the width of the beam at certain areas. And then lastly, we're going to really focus on relationships between diameter and divergence, frequency and divergence, diameter and focal depth, and frequency and focal depth. Section 9.1, Sound Beam Regions. There are 5 regions that we're going to take a closer look at for the sound beam anatomy. First, we have our near zone. That's going to be the part of the beam that's closest to the transducer before the focus. Our far zone then starts at the focus and extends away from the transducer. And the focus is going to be where the beam is narrowest. We also have the focal zone, which extends equidistant into the near zone and into the far zone. And then we'll also talk about the focal length, which is the distance from the transducer to the focus. Let's go ahead and take a closer look at all 5 of these areas in a little bit more detail and talk about how they're all related to one another. Let's start with the near zone. So the near zone is the very top of the beam, the spot that is closest to the transducer and ends at the focus. It has 3 names: the near zone, the near field, and the Fresnel zone. So it is going to be this area starting from the transducer, ending at the focal point where the beam becomes narrowest. So the near zone is the near field, and it's the area between the transducer and the focus. The widest the near field will ever get is going to be equal to the diameter of the element. Now another term for diameter of the element is going to be the aperture. And that often is abbreviated as D for diameter of the transducer. So for example, if you're given that the diameter of the element is 5 millimeters or the aperture is 5 millimeters, then the widest that near zone is going to start at is 5 millimeters. It cannot start any wider than what the crystal size is. Looking at these names as well, near zone and near field are relatively common sense. It's the part that's closest to the transducer. Fresnel zone might be a completely new and off-the-wall term for you. Just as a little preview to the far zone, we are going to have another term similar to Fresnel zone. Far zone is the Fraunhofer zone. So for Fresnel zone, I think of fresh. This is the newest part of the beam, the part that's coming directly out of the transducer. That might help you to remember Fresnel goes with near zone. Another thing you can try is the NE in Fresnel matches up with the NE in near. Next, we're going to talk about the near zone length. So we know that the near zone is this whole area from transducer to the focal point. We also have an idea that there is a length in here too. We want to know how far is it from the transducer to the focal point. So the near zone length has 3 names as well: focal length, near zone length, and focal depth. So that should help to remind you that these are all length ideas, millimeters, centimeters, some sort of length unit to describe where the focus is in comparison to the transducer face. We consider this beam to be what we would call unfocused, and that means that the element isn't curved, there's no lens, and there's no electronic pattern choosing where that focus is. But because of physics, the beam itself will naturally start to converge and get to a thinnest point, and that thinnest point is our focus. So again, the near zone length or focal depth is the distance from the transducer face to the focal point or the narrowest part of the beam. the near zone length can actually be calculated. When we are working in soft tissue, we know that the near zone length is going to be based on frequency and the transducer diameter. If either diameter or frequency increase, then what we are going to see is that near zone length is going to be deeper, or is also going to increase in value. And that is because of this formula. So we have the near zone length in millimeters is equal to the diameter squared multiplied by the frequency in megahertz, all divided by 6. And again, this only works for soft tissue, but the biggest thing that you need to take from this is that diameter and frequency are both directly related to the near zone length. We're actually going to cover this in quite a bit of detail in a couple sections. Moving forward then, we have the focus. So the focus has a bunch of names as well. We can call it the focus or the focal point. It is also known as the end of the near zone. Remember that was transducer to focus was near zone. It's the beginning of the far zone. And then we'll also see that it's the middle of the focal zone. So not only can the focus be described as the thinnest part of the beam, but we can describe it as the end of the near zone, beginning of the far zone, or the very middle of the focal zone. So in regards to the focus, we will see that the focus is where the beam is narrowest. And we're also going to see that the focus is equal to half of the diameter. So remember our crystal diameter was D. Half of the diameter is where that focus is at. So again, let's say that we had a 10 millimeter transducer diameter. The beam coming out of that will, at its narrowest, become 5 millimeters because it is half of the diameter of the transducer crystal. Next up then we have the far zone. So the far zone is going to start at the focus. Up until this point, the beam has been converging. It is going to get its smallest at the focus and it's going to start to diverge in the far field. As you can see, the far field also has 3 names. So we have the far zone, far field, and Fraunhofer zone. So just like Fresnel, we have kind of that interesting name. The Fraunhofer zone, I've always thought of like off in the distance, so that makes me think of into the far field. We also have the FRA, mix that up, you can get far, so far kind of go together as well. So you'll want to know all of these other names for this portion of the beam. So the narrowest that the far field will ever get is the focus. It's going to start to diverge, which means to widen out as it leaves the transducer further and further. And we'll see that far field continue to diverge pretty consistently until it widens to the point that it's no longer useful for ultrasound, or it will attenuate until it's no longer useful for ultrasound. As far as measurements go in relation to the far field, we know that at 2 near zone lengths, the beam is going to diverge back to the size of the diameter of the element. So remember, we started out with D for diameter. That is how big the transducer crystal is. The beam comes out, converges naturally to that half diameter. And when we get to the focus, that's our near zone length. So transducer face to where it's half of the size of the diameter, that's our near zone length. Once we go through another near zone length, the beam will have diverged back to the same size as when it left the transducer. Then after this point, it's just going to keep getting bigger and bigger and bigger. So let's do another little example. Say we have a diameter of 12 millimeters and a near zone length of 5 millimeters. So our diameter is 12. That means our focus is 6. And after we've gone 5 millimeters plus another 5 millimeters, we will see that the beam again will have widened back up to that 12 millimeters. So it goes from 12, converges to 6, diverges back to 12, and then continues beyond that 12 for the rest of the far zone. Near zone length will be equal on either side of the focus to tell us where that far field will meet up again with that diameter width. Now the amount of divergence that continues after this point is also dependent on the transducer diameter and the transducer frequency. And we have another formula that goes along with that. This one's a little bit more involved, but we have the sine of the divergence angle is going to be equal to 1.85 divided by diameter multiplied by frequency. So this formula is why we know that the diameter of the crystal and the frequency are going to be responsible for determining how much divergence occurs after the two near zone lengths. So we will talk a little bit more about the relationship of how much divergence occurs in a couple sections. So we're going to put this formula in our back pocket for the time being. Just remember that the far zone starts at the focus, widens or diverges to the crystal diameter, two near zone lengths into the beam, and then after that it just keeps diverging. Our last section then is the focal zone. So the focal zone is the area of the beam that is mostly narrow. We can see that as the beam comes out of the transducer, we're kind of wide up here, starts to converge, we're getting into a relatively narrow spot. We get to our focus and it starts to diverge, but we're still relatively narrow. And it'll get to a point where it's just quite a bit wider. So that focal zone again is where the beam is relatively narrow, the focus is in the very, very middle of it, and the focal zone is going to extend equally into the near zone and into the far zone. So say this is our focal point and the whole focal zone is 4 centimeters. We're going to see 2 centimeters into the near zone and 2 centimeters into the far zone because it is equidistant into either side of the focus. Clinically, the focal zone is very important because this is where we're going to get some of our best detail resolution from our transducer. Anywhere that the beam is narrow is going to prove better for our lateral resolution. So understanding that we have a relatively narrow area of the beam around the focus is important for where we decide to place our focus. Next up, we have 2 practice problems in the workbook. We have a 12 megahertz transducer that's 8 millimeters wide, and we have a 6 megahertz transducer that is also 8 millimeters wide. We're going to use the element width and the frequency to kind of discover a little bit more about the diameter, the near zone length, the focus, the far field diameter, and what happens in the far field. Make sure you try to work through your practice problems. When you're ready, come on back. We'll go through the numbers and then also head to the board to do some of that math. If you haven't already, please make sure to go back and work through all these problems. See if you can work through them before we go through the answers. If you are ready to go though, I will get to those answers. So our first practice problem says that we have a beam that is created by a 12 megahertz transducer that has an 8 millimeter wide element. And we need to answer the following. So the first question asks us, what is the width of the beam as it exits the transducer? So it wants to know, what is D? What is the near zone width right as it comes out of the transducer? Well, that's 8 millimeters because it equals the element diameter. The next question asks us, at what depth is the focus? We are going to use our formula down here to determine that. So diameter squared is 64 multiplied by the frequency of 12, all divided by 6, and we will see that the depth of the focus is going to be at 128 millimeters or 12.8 centimeters. Next question says, how wide is the beam at the focus? Our answer is 4 millimeters because it is half of the diameter. So if we started at 8 up here, half of the diameter is 4 millimeters. Next question asks us, at what depth in the far field does the beam diameter equal 8 millimeters? Well, 8 millimeters was our diameter, and we know that if we get to 2 near zone lengths, we should return to that 8 millimeter width. We already calculated that one near zone length was 128 millimeters, because that is the depth that the focus is at. So 128 plus 128 is 256. So the beam will return to 8 millimeters in width at 256 millimeters or 25.6 centimeters into the travel. Now this next question might be a little bit tricky, so you might want to stick around for the math on this one, but the focal zone starts at 9.8 centimeters into the beam. Where does it end? We know that the focal zone is right centered around the focus, so we should have equal distance into near zone and into the far zone. So 9.8 centimeters is 3 centimeters into the near zone, so that means it has to go 3 centimeters into the far zone. If we started at 12.8 centimeters for the focus, we just need to add 3 to that, and we will get 15.8 centimeters into the far zone. So the near zone starts at 9.8, and will end at 15.8. Our last question then is, what diameter is the beam at 30 centimeters? This one might have thrown you off a little bit because there honestly isn't a good answer other than that it's just greater than 8 millimeters. We know at 25.6 centimeters, we are back to 8 millimeters. The only thing we really know back here, and the only thing you really need to know back here, is that it's going to widen more than the diameter of the transducer after this point. Had this been a multiple choice and I gave you the options of 6, 7, 8, or 9, the correct answer would have been 9, because you just needed a number that's greater than the diameter, or greater than 8 millimeters in this case. I'll go ahead and show you the answers then for our second one. All the same questions, just different numbers, and really the only different numbers that we dropped to a 6 megahertz transducer. So same idea, we've got the 8 millimeter diameter. Plugging our numbers into our formula this time though, we get a 64 millimeter near zone length, or a depth of 64 millimeters or 6.4 centimeters of the focus. The beam width is still 4 millimeters at this point. The depth at which we get back to the 8 millimeters is 2 near zone lengths. So that's 64 multiplied by 2, which gives us 128 millimeters or 12.8 centimeters. And same idea with the focal zone, we are equidistant into near zone and far zone. So if we start at 3.4 centimeters, that means that we are 3 centimeters into the near zone, so we need to go 3 centimeters into the far zone. So our focal zone is going to end at 9.4 centimeters. And then lastly, same idea with the last question and the last slide, asking what the diameter of the beam is at 15 centimeters. That is beyond our 12.8 centimeters, and so all we know is that it is going to be greater than 8 millimeters. So I know I walked through that pretty quickly. If you want to hang around and see the math of it, we're going to go over to the board and go over how to calculate, and I'll draw a little bit more out for you so you can see the process in figuring all of these out. If all the math makes sense to you, please feel free to jump forward to section 9.2. All right, welcome to the board. We are going to walk through these practice examples with a little bit more drawing, a little bit more math being shown out instead of just walking you through it verbally. So our question here says a beam is created by a 12 megahertz transducer that has an 8 millimeter wide element. So our transducer is 12 megahertz and our element is 8 millimeters. So D is going to be equal to that 8 millimeters because the element width is the diameter that we're interested in. And our first question says, what is the width of the beam as it exits the transducer? So this is a concept of the near zone that you just need to know. You need to know that the widest the near zone will be is the diameter or the aperture of the element. We were told that it's 8 millimeters wide, so that is the widest that this beam can be as it leaves the transducer. So the correct answer is 8 millimeters. The next question is asking, at what depth is the focus? So the focus is right where the beam is becoming narrowest. And we know that that is at the end of the near zone. It is a near zone length away. It's beginning of the far zone. We have a few ways that we can refer to the focus. But this formula down here is the near zone length. And if the near zone ends at the focus, then it makes sense that the near zone length is equal to the focal depth. So we are going to use this formula to also calculate focal depth. And remember, that was a synonym for our near zone length as well. By plugging in the numbers, we are going to get 8 squared multiplied by 12, the frequency of the transducer. We're going to divide all of that by 6. So we have 64 times 12 divided by 6, and we will get 128 millimeters, or if it's easier to think of, we can think of it in centimeters, which is 12.8 centimeters. Next question down says, then how wide is the beam at the focus? And this is another concept that you need to know. If our diameter starts at 8 millimeters, the thinnest this type of beam is going to get is 1/2 of the diameter. So we need to take this 8 millimeters and divide it by 2. 8 divided by 2 equals 4. So the width of the beam at the focus is half of the diameter, and in this example is 4 millimeters. The next question down asks us, at what depth in the far field does the beam diameter equal the 8 millimeters? So remember, we have 8 millimeter diameter coming out. We traveled 128 millimeters to our focal point. The beam is going to diverge at the same rate that it converged. So if we travel another 128 millimeters, or another near zone length, we should reach a width that is equal to the diameter. So 2 near zone lengths is going to be equal to the diameter of the element. So 128 plus 128, or 128 times 2, gives us 256 millimeters, or 25.6 centimeters. Now the next question is a little tricky, and this one says, if the focal zone starts at 9.8 centimeters into the beam, where does it end? And this is going to come back to understanding what the focal zone is and how it relates to other structures in the beam. So remember, our focus is in the center here. It is the end of the near zone, it is the beginning of the far zone, and it's the middle of the focal zone. So the focal zone needs to extend equally into the near zone and equally into the far zone. We calculated that the focus is at 12.8 centimeters, and the beginning of the focal zone in the near zone started at 9.8 centimeters. So we have a difference of 3 centimeters from the beginning of the focal zone to the focus. A key concept of the focal zone is that it extends equally into the near zone as it does the far zone. So we want to know, where does the focal zone end? Well, if we've got 3 centimeters into the near zone, then we need to have 3 centimeters into the far zone. So we can take 3 and add it to 12.8 to get 15.8 centimeters. So our focus is 12.8 centimeters in, and our focal zone expands from 9.8 centimeters to 15.8 centimeters for that focal zone. So that is our answer for this one. So for calculating the focal zone, make sure that you are understanding that the focus is at the very center of it. If you had to calculate it, it'll either give you a value of one side, or it might give you a value of both sides. Had we said the focal zone is 6 centimeters, where does it start? Where does it end? You'd subtract 3 to get the start and add 3 to get the end, because it's going to be equidistant into both near and far zones. Our last question then asks us, what is the diameter at 30 centimeters? The last diameter that we figured out in the far zone had us at 25.6 centimeters here. And so now it's wanting to know, where are we at 30 centimeters? And this is going to be more of a conceptual answer versus a concrete, discrete value. And really all that we need to know is that that beam is going to keep diverging as it leaves the transducer. And so all we need to know is that anything past 2 near zone lengths is just going to be bigger than the diameter. So we know that at 30 centimeters, the beam is just going to be more than 8 millimeters in width. As I had mentioned when I was kind of walking you through everything, if we were to do this as a test question, maybe answer A would be 10 millimeters, 7 millimeters, and 5 millimeters. By logical reasoning, if we know that anything past 2 near zone lengths has to be more than the diameter, then the only one that fits that is our 10 millimeter option. So A would be the correct answer for that one. So either greater than the diameter if we're more than 2 near zone lengths away, or choose the answer, the numerical value, that it's over the diameter of the crystal. Working through the second practice problem will probably be a little bit easier because we've already calculated a lot of stuff and we talked about a lot of the concepts that we need to get the right answers. The only thing we've changed this time is that we are now working with a 6 megahertz transducer. We still have an 8 millimeter diameter, which means our focus is 4 millimeters. 2 near zone lengths away is 8, and anything past that is going to be greater than 8. So that was all things that we can get from just knowing the diameter of the transducer, or the diameter or aperture of the crystal. So our first question says, what's the beam as it exits? Well, we know that's 8 millimeters, so we can write that in. Now this is going to be a new one that we need to calculate because we've changed our frequency, and the near zone length is based on frequency and diameter. So we are going to take our diameter again, 8 squared, multiplied by 6, our frequency, and divide all of that by 6. 8 squared is 64, multiplied by 6, and then divide by 6 is actually going to equal 64 millimeters, or 6.4 centimeters. So this distance is 64 millimeters. And if that's the near zone length, another near zone length distance then would be another 64 millimeters. So we can label our diagram with that value. Now the next question down says, how wide is the beam at the focus? We already figured that out. So we know that's 4 millimeters because it's half of the diameter. Next question, at what depth in the far field does the beam diameter equal 8 millimeters again? So we know 8 millimeters, 2 near zone lengths, so 1, 2, we should be back to our 8 millimeters. So to calculate that depth, we need to multiply 2 times our near zone length. And that is going to give us 128 millimeters. So it's 1 near zone length plus another near zone length to get to where the beam depth is going to be equal to the diameter again. Next question down then says, if the focal zone starts at 3.4 centimeters into the beam, where does it end? So again, we know that the focus is at 6.4 centimeters into the body, or 64 millimeters. This is our focus. We were told that the focal zone started at 3.4, and we know it should be equal into the far zone. So if we are 3 centimeters this way, then we need to go 3 centimeters the other way. So we can take 6.4 plus 3, and that will give us the end of our focal zone at 9.4 centimeters in the far field. So we're going to see that focal zone being equidistant on either side of the focus, 3 centimeters into the near zone, 3 centimeters into the far zone, and that will give us that 9.4 centimeters ending area. And then our last question, what diameter is the beam at 15 centimeters? Again, we figured out that our near zone length is 128 millimeters, or 12.8 centimeters into the body. That was the last step that we were able to calculate the beam width for. So now we know anything past 12.8 is just going to be greater than 8 millimeters. Section 9.2, focal depth. In our 9.1 practice examples, we had these two transducers. We had 12 megahertz with 8 millimeter diameter, and we had a 6 megahertz with the 8 millimeter diameter as well. So the only things that are different between these two transducers are their frequencies. When we plugged in our numbers to our near zone length formula to calculate the focal depth, or the near zone length, we got the 12 megahertz transducer showing a focal depth of 128 millimeters, and the 6 megahertz transducer showing a focal depth of 64 millimeters. So by using those numbers and using our formula, we get to see one of our first relationships in action. We can now see that frequency and focal depth are going to be directly related. So in other words, as frequency gets higher, our focal depth gets deeper. And if the frequency goes lower, then our focal depth gets shallower. And we know that again because of our formula. We learned in our very first unit that when the numerator is compared to the quotient, the numerator and the quotient are directly related. And we can see that in our example as well. Our high frequency transducer has a deep focal depth. The low frequency transducer has a shallow focal depth. When this number increases, this number should increase. When this number decreases, this number will decrease. But frequency isn't the only thing on the numerator side. We also have diameter. So I bet you can already guess how diameter is related to near zone length as well. But of course, we're going to take a look at an example. So I've got two new transducers here. We've got a 10 megahertz 9 millimeter diameter transducer, and we have a 10 megahertz 3 millimeter diameter transducer. So this time I've left the frequencies the same, but the diameter of the crystals are different. And just like when frequency increased, near zone length increased, we're going to see the same thing with diameter. As diameter increases, we will see the near zone length also increase. So just by plugging in these numbers into our formula, we'll see that the 9mm diameter calculates to a near zone length of 135 millimeters, where the same frequency but 3mm diameter calculates only to a 15mm or 1.5 centimeter near zone length. So from this example, we can see again that diameter and focal depth are directly related. Again, in other words, if the diameter gets wider, our focal depth will get deeper, and if the diameter gets smaller, then our focal depth gets shallower. So let's go back to that picture again real quick, and we can see that 9mm diameter, deep depth. 3mm diameter, shallow depth. Diameter number value increases, focal depth value increases. Diameter decreases, focal depth value also should decrease. I also want to point out, because diameter squared is part of this relationship, when the diameter changes, the diameter is going to have a larger effect on the near zone length than just the frequency does on its own. So our key takeaways from section 9.2 is that the focal depth is directly related to the frequency and the diameter of the transducer. But that's not all that's related to the frequency and the diameter. Because now we have section 9.3, beam divergence. Remember back just a few slides ago when we were talking about the regions of the beam, we were talking about the far zone. I mentioned that in the far zone, the beam is going to start to diverge after the focal point. And it'll just kind of keep diverging indefinitely. But the rate at which it diverges, or the angle that it diverges at, is also dependent on the frequency and the diameter. So here is our formula. We see that the angle of divergence is going to be equal to 1.85 divided by diameter multiplied by frequency. I'd be very surprised if you actually had to calculate the near zone length, and I would be very, very, very surprised if you ever had to calculate the divergence angle. It's just not going to happen. So instead, we are going to focus on the relationships that this formula tells us. So we know from this formula that diameter and divergence are inversely related, and that frequency and divergence are inversely related. And we know that because of our formula. We've got diameter and frequency both in the denominator position, so they are going to be inversely related to our quotient. The idea of beam divergence, though, is super important for the sonographer, and that's because if we choose lower frequency transducers, that's going to cause our beam to widen more in that far field. And when we have a wider far field, we are affecting our lateral resolution. The beam width is going to have a direct relationship to the lateral resolution of the image. Now we're going to talk about lateral resolution in quite a bit more detail in the next unit. But why lateral resolution is important and why we are concerned about how wide the beam gets is because, first off, we know that the focus in the focal zone should be placed just at the area of interest or just below it. And that's because the beam is narrowest here. That thin beam improves our lateral resolution a lot. And that's really what we want. We want good detail in our images. The second problem, though, is that when we have that diverging far field, it's going to diverge to a point where it's going to really affect our lateral resolution. The beam is just going to be too wide to recognize small structures and image them appropriately. So when we choose high frequency transducers, we're going to have less divergence, which means that that is going to give us better detail with that high frequency transducer. Going to a low frequency transducer, we learned, helps us with penetration. The attenuation is much, much less than a high frequency, but then we have the trade-off of losing detail in our images in that far field. And I told you we wouldn't be doing any math with that formula. I did all the math for you. I just want to show you some examples, plugging in some numbers and looking at some diagrams. So now I've got two transducers. They are both 4 millimeters in diameter. We're going to look at the frequency change first. So we have a 5 megahertz transducer and a 1 megahertz transducer. I went through and calculated out the near zone lengths again, just to kind of prove that our low frequency has a shallow near zone length, high frequency has a deep near zone length. But this time we really want to focus on what's happening in that far field. How is the beam diverging? So we see with our 5 megahertz transducer, if we plug all our numbers in, use our calculator, use our charts, we will see a 5-degree divergence. That means that instead of continuing straight through here, it angles out just at 5 degrees and will keep going in that direction. So 5 degrees, hardly anything. Look at our 1 megahertz though. When we plug all those numbers in, we're going to get a 27-degree divergence. So instead of coming down and going straight, which would be 0 degrees, it's taking a turn at 27 degrees and will continue expanding out at that 27-degree angle. So the larger the angle, the more divergence that is occurring. So from these examples, we can see that frequency and beam divergence are inversely related. When the frequency gets higher, there will be less divergence. Frequency gets lower, there's going to be more divergence. And in true fashion, of course, we got to flip it around because diameter is also related to divergence. So we're going to take a look at these 2 megahertz transducers, but change the diameters around. So our first one is 8 millimeter diameter, a large, wide aperture. And then we have a 2 millimeter diameter or aperture. Now, again, I went through and calculated out our near zone lengths. Based on these diameters, we can see that we have small diameter, shallow near zone length, large diameter, deep near zone length. But again, we're focusing on our divergence this time. So let's take a look at what it means for how the beam looks in the far field. So now we see that our 8 millimeter diameter has barely even expanded out because once we plug all those numbers in, we'll see a 6-degree divergence angle. Compare that to our 2 millimeter diameter, which also happens to produce a 27-degree angle of divergence. So remember, it's coming down here. If there was 0 divergence at this point, the beam would just keep heading straight forward. But at this point, it turns at 27 degrees and keeps widening beyond that point. So now from these examples, we can see again that beam diameter and beam divergence are inversely related. So as the beam diameter gets wider, less divergence will occur. If the diameter gets smaller, then we're going to see more divergence. Section 9.4. Let's go ahead and review these 2 concepts in conjunction with one another. So remember, first and foremost, frequency and diameter are related to the focal depth and the beam divergence. Let's focus on our increased numbers, so our up arrows, our high frequencies and our wide diameters. High frequency and wide diameters are going to affect the focal depth and the beam divergence in the same way. So high frequency, wide diameter, we're going to see deep focuses. With that then, we also see less divergence. So increased frequency, increased diameter means an increase in the focal depth and a decrease in the divergence. Let's take a look then at our smaller numbers, our down arrows. So if we have low frequencies or small diameter transducers, we're going to see shallow focuses with more divergence. So as we decrease the frequency, decrease the diameter, we're going to see a decreased value of our focus, so shallow focus, and then we're going to see more divergence or increase in the far field. And this is the picture that you have in your workbook, kind of showing you the relationships of all of them. So if you're still looking at this and thinking, I just need another way to think about this, well, let me show you another thought that I had about this. We know that diameter and frequency are both going to be determining factors of the near zone length and divergence. Now, what I thought was kind of cool when I was going through all of this and thinking it through, I saw that near zone length, N, near zone length, has diameter and frequency in the numerator position. And we know from Unit 1 that the numerator is going to be directly related to the quotient. So near zone length, numerator position, directly related to the quotient. So as diameter and frequency increase, we'll see the near zone length also increase. The other thing that I thought was kind of cool is that the near zone length sits above where we would look at divergence. So the near zone is kind of the numerator of the beam, so it sits higher than the divergence. But then the really cool thing was that divergence also kind of helped out in this too. So we have divergence and denominator. So now we move diameter and frequency into the denominator position when we're talking about divergence. And we know that when we have denominator and quotient relationships, that they are inversely related. So if you can remember near zone numerator, and then remember that giant rule that I taught you right in the beginning, numerators and quotients are directly related, that's all you need to know. You really just need to know the relationships. Same idea with divergence. If you can remember divergence denominator, then you know that they are going to be inversely related to the divergence of the angle. And that might help you to kind of work through the values and draw all the arrows out again, should you be asked a question about these relationships. So speaking of questions about those relationships, that's going to be our practice. We are going to pause here, go through the practice part, and try to figure out which transducer in the comparisons have more divergence, less divergence, deeper depth, or shallow depth. Unpause, and we'll go through those answers. All right, again, just a reminder, make sure that you've tried these practice examples, but let's go ahead and go through those answers. So the first question says, which transducer will have a deeper focus? And we have two examples, one with diameter comparison and one with frequency comparison. So we'll just kind of go down through each one. So which transducer has the deeper focus? When we're looking at diameter, we know that deep focus goes along with wide diameter. Big diameter, deep focus. So that is going to be our 19 millimeter transducer. As far as frequency goes, we know that increased frequency provides an increased or deeper focus. So that's going to be our 12 megahertz transducer. Now the next question down says, which transducer will have a shallower focal point? So we're using some of our synonyms in here as well. So focal point is the same as the focus. We're also using aperture in this example as well. Remember, diameter and aperture are the same thing. So shallow focal points are going to go along with narrow or small apertures. So our correct answer is our 13 millimeter transducer. Next one down is comparing a 1 megahertz or a 4 megahertz. Low frequencies equal shallow focal points. So you should have selected your 1 megahertz. Next question down asks us which transducer beam will diverge more. So which will have more divergence? And we know that frequency and diameter are inversely related to our divergences. So when we have more divergence, we're looking at lower values in our numbers. So 6 millimeters versus 3 millimeters, it should be our 3 millimeter. Low numerical value will have a high divergence value. Same idea with frequency. Low frequency value is going to result in a high divergence value, or that divergence angle that we were talking about. And then our last question, which transducer beam will diverge less? So again, frequency and diameter are inversely related, so we're looking for the numbers that are higher out of the pairs. So the 33 millimeter diameter is going to diverge less than the 23 millimeter diameter because it is a higher value, a higher number. And the 17 megahertz transducer is also going to diverge less compared to the 10 megahertz transducer. Increase your frequency will decrease your divergence, inversely related. Now this last question is probably something that's going to be more similar to what you might have on a test. You might be given some frequencies of transducers and some different diameters. And then this question asks us which transducer will have the best lateral resolution in the Fraunhofer zone. So we learned that the Fraunhofer zone is the far field, and then we also learned that lateral resolution is best when the beam is narrow. So we are looking for a combination of frequency and diameter that is going to give us the best chance of having the least amount of divergence in that far field. And because we are inversely related, we're looking for our biggest frequency and our biggest diameter to create the transducer that'll have the best lateral resolution in the Fraunhofer or far field. So in this example, our 12 megahertz transducer at the 10 millimeter diameter is the best option. It's got the highest frequency out of everything, and it has the largest diameter. Section 9.5, clinical discussion. So up until this point, we really needed to simplify the beam shape to discuss some of the key features of the beam and learn how it acts in space. But for our modern clinical ultrasound, the physics is a lot more complex. So I've created kind of a Q&A to think a little bit more about what's happening in space with our beam and kind of start thinking about how this clinically applies to what you're going to be doing day in and day out with your ultrasound machine. I know when I was a student, one of the things that I was kind of confused about when we were learning about the beam shape and how everything looks is I was thinking, well, I have a knob on my machine that says focus, and I can move that around and I can change where the focus is. Has that been what we're talking about? Well, the answer for this one is actually no. The beams that we've been talking about in this unit so far, we consider to be unfocused, meaning they don't have anything that's going to cause them to focus, like a lens or curved elements or electronic focusing. And I'm sure you're not surprised by any of this. We're going to learn about those very soon. But what we are talking about with these beams is that they do have a natural focus. And that's because of two things. First, we're creating diffracted wavelets from the transducer, and then Huygens principle is at play as well. So when the PCT crystal is created, they can be made very, very small, or we might make them a little bit bigger, but within that bigger PCT crystal, there are going to be very small sound producing points. It's not that the whole crystal just creates a sound beam, it's that there are these tiny little spaces within the PCT crystal that are actually going to produce the sound beam or the pressure wave out of the PCT crystal. When sound comes out of a very, very tiny area, it takes on more of a V-shaped wave. So we have this example here. We can see the pressure changes are happening on the PCT crystal. This tiny little crystal is creating this V-shaped wave. So these are V-shaped waves, also known as Huygens wavelets. And this V-shape that we get out of here is the diffraction. So if we had this pressure kind of coming through as a wide point, once it hits this very small structure, it diffracts and creates these tiny little wavelets. So we are either creating tiny little wavelets out of single small PCT crystals, or we're creating lots of little points of sound in a larger crystal. And what ends up happening is those tiny little wavelets are all going to come out and they're all going to interfere with one another. And that's where Huygens principle comes in. Huygens principle tells us that as these waves interact, they're going to interfere both constructively and destructively. And what's going to result is that natural focus or hourglass shape to the beam. So a completely unfocused PCT crystal will have a natural focus. The problem is that that focus isn't always where we want it. So we have discovered if we introduce lenses, curved elements, or electronic focusing, we have more control of where that focus is. Another thing that may have crossed your mind while we were talking about frequencies and focal depth and divergence is that high frequencies have those deep focal depths. And you might be thinking to yourself, but we use high frequency transducers to image shallow, so shouldn't they have a shallow depth? And yeah, that might be what you would think at first, but we learned in this unit that the physics tells us that that higher frequency has that deeper focal point and less divergence. But we also learned that those high frequency transducers are going to attenuate really quickly too. So a lot of times they're going to attenuate before we get any meaningful information from their deep focal points. But on top of that, there's more physics that tells us that that small diameter is going to have a bigger effect on that near zone length than the frequency will. So if we can make high frequency crystals that are very tiny, that's going to bring that focus up and make it more shallow. So knowing this, when manufacturers make the transducers, those high frequency transducers are going to be made with tinier crystals to bring that focus up to a more useful depth. So just as an example, one of our highest frequencies that we use in medical ultrasound is 17 megahertz. If we had a transducer with an 8mm aperture on that, it would have a focal depth of 18 centimeters. That 17 megahertz transducer is going to be gone long before 18 centimeters. So instead, we can turn that around and make it a 17 megahertz transducer with a 1mm aperture. Now we're looking at a transducer that only has a 2.8 centimeter focal depth. And that is going to be more conducive to using that high frequency for those superficial, shallow structures. At the beginning of the lecture, I had mentioned that we're going to look at diagrams as if these are all single element continuous wave transducers. And now you might be wondering, well, what does a pulsed wave transducer beam look like? And to be honest, it's really not that much different. It's just a matter of where the beam is in space compared to that pulse. So if we look at these two images, the one on the left is our continuous wave. It's just always there. It's always getting electrical voltage, making a sound wave, beams coming out constantly. On our pulse waves, that electrical voltage comes down, interacts with the PCT crystal, and a quick, short pulse is sent out. But that pulse has to travel in space over time. That's how we get that hourglass shape. It has to move out of the crystal, through the near zone, to the focus, and then into the far field. And that'll happen, but it happens over time. And because the pulse stops, the beam will also stop. And then it has to kind of reproduce that traveling again. Where on the continuous wave, it's just always constantly making that near zone, focus, and far zone. So every time a pulse comes through, near zone, focus, and far zone have to be created. It'll be created over time, and then we wait for echoes to come back. Beam is created over time again, wait for echoes to come back. Remember, we talked about the idea of pulse duration, where we have that period of time of creating the pulse going out, and then we have our pulse repetition period, which is the time creation plus the waiting time. So same shape, just a difference of waiting for the whole pulse to be created. Now, this may not have been something that you were considering, but it is at least worth mentioning because this is going to have actually a very large clinical impact on you as a sonographer. So is the intensity the same all the way through the beam? So the drawings that we've been using so far show the beam narrowing at its natural focus. And it would make sense that as the beam narrows, we are going to see more intensity, because if you remember back to your intensity formula, intensity is equal to the power over area squared. So if we're reducing that area or the width of the beam, we are going to see an increase in the intensity. So for the most part, we will always say that the focus, the narrowest part of the beam, is the most intense part of the beam. However, it gets a little bit more complex than that when we are actually using the beam in soft tissue or in a medium that's going to cause attenuation. So again, all the images that we've been using are not taking attenuation into account. So we're acting as if they could just go on and on and on forever. But that's not true in the clinical setting. The beam comes in, it's going to lose some of that power because of attenuation, but it's also going to gain some of that power because of narrowing. So there's a fine balance of losing intensity and increasing intensity based on how far the beam has traveled and the width of the beam. So in reality, what we see is the strongest point is actually just above the focus, and that is because attenuation hasn't quite gotten to the point of reducing that intensity to counteract the amount of narrowing that will occur at the focus. So again, if we think about it, we've got the sound coming out of the transducer. It's attenuating along this line. So it is getting weaker as we go through. So this part of the beam, attenuation-wise, is stronger than this part of the beam. But the second factor that we need to look at then is what's happening to the area. We have more area up here compared to the less area down here. So now if we're just looking at area, we've got less intensity here because of the larger area compared to the intensity with the narrow area at the focus. So again, attenuation-wise, more intensity, less intensity. Beam width-wise, less intensity, more intensity. Combining these two thoughts together then tells us that right above the focus ends up being the most intense part because we still aren't attenuating all the way through this area, but we are still experiencing a reduction in area. And this idea is actually very clinically significant because we often will tell you as instructors that you should place your focus at or below the area of interest. So over here we have our focal zone on a machine. If you have this little I-bar shaped cursor on the side, this usually represents a focal zone. If you just have like a little arrow here and not the spacer, that usually represents a focal point. So the machine is showing us a focal zone here with the focal point in the middle of it. And when we are using a transducer and an ultrasound system that allows for focal point movement, we will want to take this and move it just at or just below the area of interest so we can utilize that intensity and the narrowness to provide the best image, because our stronger beam is going to return better echoes and that narrow beam is going to provide better lateral resolution, which helps with our detail. The concept of the focus and lateral resolution we're going to talk a lot more about in the next unit when we get into our resolutions, but this is a nice kind of little precursor about why we need to think about how that beam is changing in space and the intensity within that beam. Remember in this unit we had been talking about single element transducers creating one continuous wave beam. Now we know that continuous wave beams cannot create images, but we did just kind of get done talking about how pulsed wave beams look very similar to our continuous wave beams. And we know that our pulse wave beams do create images. I think it's easy for students to kind of look at how quickly our pictures are made and how seamless it seems and think that maybe just that one beam coming out of the transducer is creating the whole entire image, but that's not true. What ends up happening is that one beam is going to create one scan line. And then we put a ton of scan lines together to create the full frame or image. This is also a great opportunity to point out that our modern transducers have multiple PZT crystals, not just the one crystal that we've been talking about so far. So as we learn about transducers, we're going to start to learn more about how the PZT crystals work together to create a beam or a scan line. And then we'll learn more about how the machine creates each scan line to create a full frame. And it's just amazing how quickly the machine can do that and make it look like a seamless movie to our eyes. So there's lots more to come on the image creation and the beams and the PZT crystals all working together. This is a great jumping off point of taking that knowledge of these single element transducers, and now we're going to see how to apply them to our multi-element transducers that we use currently. And that brings us to the end of Unit 9, Beam Anatomy. So make sure to head back to your workbook and work through some of those activities that we have in the back. Review the nerd check questions. Again, those are open-ended questions that you can use to test your knowledge and recall the information that I presented in this unit. Remember, we had some big formulas in this unit, but it's the relationships that we can pull from those formulas that are going to be ultimately what you need to know. And just like the transducer anatomy, be prepared to be able to label anatomy and talk about each region and how they are related to one another.